Hello, everyone. Welcome to our session. Today, we're going to talk about how to run a cost-optimized LLM inference backends with heterogeneous fleets on Kubernetes using AWS AI chips. My name is Yahav, and together with me, I have Liangfu. We both work in the Annapurna ML team over at Amazon. So let's get started with the problem. As AI adoption grows, we are seeing more proof of concept turns into more stable deployments. And some will say production, some will say staging, depends on how you defer it. But it is basically, in simple words, more serious deployment. And that entails more redundancy, more availability, more SLOs. And that translates into cost. And this is becoming a challenge. And the cost per token is the key metric that customers are care about. At the same time, many teams are constrained by sometimes limited compute options, often relying solely on GPU. Now, that can create availability constraints and limits flexibility in demand spikes. Now, the challenge here is the combination of both. How do you balance the cost and performance with availability and all the things that production deployments entails? So, to solve the cost-performance availability balance, we will combine flexible models, flexible pricing models, and models not the PyTorch models, but actually cost models, with heterogeneous compute pools. Now, on the cost side, Amazon, as well as other cloud provider, offers roughly three main offerings. The first one is on-demand, where you just start the node and you start using it. And the second one is savings plans. Savings plans is basically if you are absolutely sure about how much compute you will need, you will purchase it and you will get 60% off, roughly speaking, of the on-demand price. But what if you don't want to? You're in the on-demand area, and the on-demand can be pricey. EC2 Spot is another option that we offer. And basically, this is an unused capacity that Amazon offers at a steep discount, roughly 70%. There is more accurate percentage numbers in our documentation that I will refer you at the end of this presentation. Now, on the availability side, if we are mixing fleets, compute fleets, with other options, then we can benefit from both worlds, right? And this is also, of course, when you have shortages, etc. Now, once you get that mindset in using this thing, we are applying an open, unified, open source, unified ecosystem that can leverage PyTorch. On top of that, then below that, we have vLLM as the invocation platform, and then we have Kubernetes that powers the CUDA SDK as well as as Neuron. So let's start with how we can expand the compute options. Like I said, until now, many teams were primarily focused on GPUs. Now, what is changing here is that now you can unlock additional accelerators, Trainium alongside the GPUs. Now, Neuron is the software that powers Trainium. It brings predictable and cost-efficient inference capacity, while GPU remained a familiar compute options. The key value comes from using both at the same application. Now, vLLM is the serving abstraction. of the same PyTorch models, and then you have this backends that are powered by either Neuron or CUDA, and then Kubernetes, CUDA, and Carpenters are basically the miscellaneous packages, components that helps you to go and build and shift traffic, allocation resources, and so on. And we're going to see all of that in a second. Okay, now before we continue, I just wanted to make it clear, this isn't about benchmarking one side on who is better and or replacing one. It's about running those side by side. Okay, so I'm going to start with a quick demo. I don't know how I'm going to do it while I'm holding my mic, but let's see. So I'm going to speak up, and so hopefully you're gonna hear it. So I'm going to start with. Okay. So I'm going to discover the endpoint of the application that we built. Oh, okay.
I start sharing the slides.
I'm going to stop sharing. Thank you. Okay, thank you. So, yeah, I'm going to do it here. I'm going to do this. Okay, serve. So what we have here, this is a simple application that has 4 backends. Each backend is serving a model with a specific hardware. It's either GPU or Inferentia or Trainium instance. In our case, we have L40S GPUs and Neuron. To make it interesting, we deployed two models. One is the Llama 8B, and another one is the Qwen 3 8B, just to give you an idea. And let's write something. Paris is a city. So I'm going to run that, and that will return a result. So I'm going to run it again, so you can see that it's fairly came back at the same time. And if we want to look at the time, you can see that the GPU was a bit faster on the total time, 0.39 compared to 0.30 on GPU. But on the other hand, the time to first token was a bit faster on the neuron side. So again, I want to make it clear, this is not us benchmarking who is better and who is not. It's more about making a comparable deployment unit that you can go and apply the concept that we are about to discuss. So that's how it looks like from first, like just to give you a taste of performance. From operational perspective, I want to give you more idea. So I'm going to just pick one of the four. These are the backends, the native one and the one with the GPU and the one with the Neuron. Each one load each instance. So I'm just going to log into one of the instance. So I'm just going to pick up on this. This doesn't matter. So this is GPU, so I'm going to use NVI top, right? And so what you can see, the model is sharded across 4 cores, and these cores are fully committed here. And if we run, I'm going to make a trick here. So I'm going to run a consecutive runs here, so it's going to run a bit slower. So you can see how the cores are saturated up to roughly 87–85%, right? And that's about the GPUs. And let's look at how does it look like on the Neuron side. I'm going to pick up that one. It's the same thing. And with Neuron, we don't call it NVI top. We have Neuron top. And you can see that it's fairly similar, right? We have four nodes. 4 devices. Each device in our case has 2 cores. And here you can even see how you can actually go and look at the memory map of each core. But the point I'm trying to convey is, I'm going to run it again so you can see that's you can see that it's a fairly similar usage. And the interesting point here is that you can also see from tooling perspective that it's feeling the same. So we saw the performance, we saw some tooling, and let's look at the price. Okay, so we can do. Okay, I want you to focus on the first 4 because the last 2 are M5, which are basically the miscellaneous instances that powers the Gradio app and other loader that are serving this demo. But essentially, what we can see here is that we have 1 instance per model, just to make it clear in the demo, but this doesn't have to be. You can still host many models in the same instance. But the interesting point that we wanted to appreciate here is that the same performance that you saw before on the G6E cost roughly $10 per hour, and on the Inferentia 2 costs $6, and this is roughly speaking 30% off. And if you look at the last one, the last Inferentia 2 deployment, that cost 2.7, which is the 70% that I mentioned before. And that's because this instance is powered by a spot instance and not on demand, as it's mentioned before. So some might ask, okay, so first of all, well, 2 questions. First question is why you didn't run the G6E on spot. That's valid. It's totally doable, and you should do it if you can. I'm sorry, you can do it. It's the same method, but that's the first question. And to answer that, you need to explore the options before using spot. And for that, we have. Turn off this thing. We have a website called an Amazon EC2 Spot instances. You can just look at up on Google. And what you see here, it's a table. Now, I wanted to make it clear that this table does not mean that it's super accurate and it's super online, but it's supposed to give you an idea of what was the frequency of interruption, as you can see here. And if you are considering G6 instances, let's say, so I'm going to just write G6. And so you will see the frequency, historical frequency of interruption. And since we use the G6E12 XL, you can see that the chance of interruption is 20%. And it's still doable solution, but it's going to be more frequent interruption. But if you look at Inf2, for example, and the one that I choose, which is the 24XL, the chance of the frequency of interruption, the historical one, was less than 5%. That made me to decide of the demo to demonstrate a spot with Inferentia. That's all. Okay, so it's all the methods that we are open sourcing, announcing today, and open sourcing it are valid for all the options. Okay. Another thing that I wanted to say. Okay, so what happened when our container, our backend is getting interrupted? So for that, we created some sort of a simulation, a workload simulation, that keeps running a load against these four endpoints, right? And you can see the RPS, the request per second. You can see the latency. You can see the TTFT and the number of nodes that are alive and serving it. And just the details that I want you to appreciate from the RPS, latency, and TTFT is that it's fairly the same, right? The same point that I was making when I was using the Gradio app. But if you look at the node alive, you can see that the total number of nodes alive are 6. Remember that I ask you to ignore 2, so we have roughly 3 on demand for serving the models, and 1 that is using spot instances. So this is in the last 1 hour, it was pretty good. The last 12 hours, what was pretty good. And what happened in the last 24 hours? There was a point where the number of nodes that went up of the spot is because that there was an interruption or rebalance notification. And what does it mean? It means that we build our system, our containers, to listen to rebalance notification. And that, when the rebalance notification arrived, we basically send a sync kill to the SIG term, to all the containers, and basically that recovery step started. And the results of it, after the duration of that time, allowed the endpoint to start again and recover. This is a view of 3D, so you can actually get an idea of how those interruption looks like, right? Now, I wanted to make it clear that although that I'm talking about spot instances, this is not limited to spot instances only. This is a practice that you should apply regardless, right, of being more resilient and so on. Okay, so I'm going to go back to the presentation. And so by now, what we did, we took our AI application and we validate the model. Validate the model configuration and performance. The next step is to find the breaking point. The next step is to find the breaking point of that application. And what does it mean? It means that we took that minimal deployment unit and we started to load it with a synthetic workload that adheres to the shapes of the load that we think that our customers will do, our users will do. And we built several configurations. And what we found, and so we loaded up until the point where the latency go above acceptable level, right? And when that happens, that was the breaking point. So that is the 5 numbers that you can see marked in the upper graph. And what we've done with this, And what we've done with this, we created 5 CUDA objects. CUDA is an open source project that's in the Kubernetes open source that basically allows you to go and watch an RPS per deployment unit and increment or decrement the amount of required pods, required model units that you need, right? And that's how you reflect the user demand into the system. Now, the CUDA objects will work both ways. So if the RPS, the breaking point that I mentioned, will cross the line as it goes up, it will increment, and when it goes down, it will decrement the amount of pods. Now, at this point, the Kubernetes will tell you, hey, I need X amount of pods, whether it's going up or down. And then it's up to Carpenter, which is our vending, open source node vending solution, will seek to bring you the instances that's going to power those model backend. Now, the interesting point here is that Carpenter you can, in the declaration of the node pool of Carpenter, you can inject logics like many pools, fallback like priorities, smart scale down, and cost efficiency. And we're going to see that in a second. I'm not going to show you the entire solution here, but just to give you an idea, we ran this simulation, and we found that at the point where the red line is running out of capacity, Carpenter took over and basically take care of the resources, of the resource allocation, and eventually reset when the resource allocation was finished. We injected that synthetically by setting limits. Okay. Yeah. So that's what we have from the platform perspective. Now I'm going to pass it over to Liangfu to talk about advanced configuration. Liangfu.
Yeah, thanks, Yahav, for the explanations. So far we've been explaining how to shift the traffic and doing the fleet-level orchestration. Let's say we wanted to look into how we can optimize the model on a PyTorch model and to run it on Neuron. So if we, the typical way of doing that is like we take a PyTorch model and we build a package called NxDI, which is Neuron X distributed, and then the NxDI package is going to generate actual graph along with the kernels. The kernels we build is called NxDI kernels, which we'll cover later on, and produce the neuron executable. The neuron executable flow is basically to orchestrate the flow from device placement and graph optimization along with producing the neuron executable along the way. And this is kind of on top of that is this provides the capability of the running continuous batching, speculative decoding, as well as distributed parallelism. So these are enabling a larger scale capability of running inference. So all of these are integrated with vLLM so that the workers, the neural workers just work the similar way as GPU workers so that we don't need to break anything in the orchestration fleet for the running purpose. If we see a bottleneck in the profiling stage, let's say we're running a neural model on a PyTorch model on Neuron, we're going to use a so-called NxDI, which is like neuron kernel interface. It can help us program with lower level intrinsics to program the hardware without, and then expose the interface to PyTorch. Then we'll have the capability to use PyTorch and then inject those bottlenecks with higher level abstraction while having the capability of using low level hardware intrinsics to speed up the performance. And the workflow is straightforward. We use profile to see the potential bottlenecks, and then it programs NxDI, inject that as PyTorch, and expose that to NxDI, and then run with a vLLM. And then NxDI will handle core placement, and we use touch level data parallel to handle the multi-dynamic batching problem. So to summarize, there are two levels of optimization. At the flat level, we'll see we can use Kepler, CUDA, and Kubernetes to orchestrate the dynamic scaling problem and to shift traffic dynamically. And the model execution level, we can use the NxDI, so-called neural distributed inference package, and do the graph lowering and runtime execution. When necessary, we can use the neuron kernel interface to program the hardware primitives and do more performance with lower hardware engineering. And so today we showed the potential fleet with shifting traffic, and then we demonstrated the potential of leveraging 70% cost reduction, again, with the shifting traffic, depending on the actual fleet availability with the spot instances available. So next step is to explore the documentation on neuron docs, and then take the experimental on EKS examples on GitHub. I think last but not least, we are kind of hiring. If you are interested, please reach out to us, and we can reach out to the right team. Thank you.
We can answer a question. Sorry. Do we have time, or should we take it down? Okay. Okay. So the question was, is that open source? Is that can be reusable? The answer is yes and yes and yes. We are publishing samples on this repo that you see here, but we also have other more specific, scenario-specific, like the one that Liangfu mentioned, speculative decoding and all, and soon disaggregated inference and other tutorials in the Read the Docs website. So it's all open source. Now, to the second part of your question, whether we can run it on CPU, on GPU, yes, that's definitely, yeah, it's exactly what I showed you here. This is running on GPUs. Yeah. You're welcome. One more question? Okay. All right. Thank you very much for. Oh, yes, please, please, please. It's so the answer, the question was, how do we scale the resources? When I mean resources like nodes, when we bring nodes per type, whether it's based on some declarative number. and so no, it's all good. And so the answer to that is as like I said, we're going to have, I mentioned 5 variations, right? Remember that I showed you 5 variation, like this one, right? This one, yeah. These 5 variations. So for each variation, we are going to create a node pool section, and we're going to declare on that node pool that we want that this node pool going to launch an Inferentia 2. And another one will say, I want you to launch GPU and the specific type. And you can also specify what type of pricing model you can say, on demand, on spot. And the cool thing about Carpenter is that you can mention both, and Carpenter will be smart enough to say, if I have capacity, I'm going to bring it to you, and if not, I'm going to fall back to on demand. So it is zero effort from you managing this, what I just said, all these words, okay? Now, the beauty of all of that is when you put all of this together, let's say, let's look at the point where we induce limits on the red one. The red one is the most cost performant. I specified for Carpenter, use this pool all the time because this is the one that gives me the best performance for the best cost. But what happens if there is no enough capacity? Carpenter will know how to fail over between all the nodes pool that I mentioned before. So it's a declarative approach that is working through the imperative fashion of CUDA that looks at the usage. Did I confuse you, or is it? Okay, good, good. By the way, we published a paper that describes all of that in details of how we did it, and we also open source it. That was not mentioned, but that's not what I mentioned before. So I can share with you the link to the paper. Thank you very much, guys. Thank you, thank you.